We live surrounded by an invisible, chaotic world of gas particles, millions of spheres randomly colliding at high speeds. The challenge in chemistry is figuring out how to measure their macroscopic behavior from all this microscopic chaos. This is the foundational formula used to measure that behavior, the ideal gas law. The equation describes the state of a gas using 4 macroscopic observables: pressure, temperature, volume, and moles. That last variable, moles, represented by the letter N, is a raw count of the total number of gas molecules present in the system. In the ideal gas model, we track this molecule count because it is the primary driver of physical behavior. At this scale, we treat all particles the same, regardless of their chemical identity. Take this container filled with uniform red particles. It represents our physical baseline for a pure gas. The pressure inside this specific container is generated by the number of these red particles bouncing off the walls at a specific temperature and volume. If we assume chemical identity doesn't change the outcome, calculating the pressure of an ideal gas becomes an exercise in counting particles. This raises a question. How do we calculate pressure when the container is filled with entirely different types of gases? Here is our original pure gas container on the left, compared to a mixture containing 4 distinct gas types on the right. Despite the different colors, both containers possess the exact same total number of particles. Because the total count is the same, both containers exert the exact same amount of total pressure at a given temperature and volume. This occurs because ideal gas particles do not interact with one another. They move as if they are alone, meaning a mixture behaves the same way as a single pure gas. Dalton's law defines partial pressure as the specific independent pressure contribution made by just one of the gas types within that mixture. Since these gases ignore each other, the total pressure of the container is the sum of the independent partial pressures of every gas inside it. We can now translate this physical observation into a mathematical proof. We begin by writing the ideal gas law to isolate the pressure of just our original Reynolds gas A. The pressure contribution of gas A depends strictly on its specific mole count, or N sub A. For the mixed container, the total pressure is simply the sum of the individual equations for all 4 gases. To find the exact ratio of one component's pressure compared to the total pressure, we divide the 2 equations. Here, we are dividing the partial pressure of gas B by the total pressure of the system. Since the container is shared, the gas constant, temperature, and volume are identical. We cancel R, T, and V from the fraction. The result, the ratio of gas B's pressure to total pressure, equals gas B's moles divided by total moles. This ratio, moles of one component over total moles, is called the mole fraction, represented by the symbol chi. It is the mathematical way of expressing what percentage of the total molecules belong to a specific gas. If we multiply both sides by the total pressure, we can solve for the partial pressure of gas B. This completes the proof. A gas's partial pressure is mathematically proportional to its concentration inside the mixture. We apply this math to the largest gas mixture in our daily lives. At sea level, Earth's total atmospheric pressure is exactly 1 atmosphere. This photograph shows the atmosphere as a single unified layer of gas. In reality, it is a mixture where nitrogen gas makes up about 78% of the total molecules. In our formula, that 78% becomes a mole fraction of 0.78. A quick calculation tells us that nitrogen's individual contribution to the air pressure around us is 0.78 atmospheres. This ratio allows us to calculate how much of the atmosphere's total pressure is exerted by each specific gas in the mixture. We can also use these mole fractions to find the combined pressure of multiple gases at once. Suppose we have a container with 4 equally distributed gases at a total pressure of 10 atmospheres. If we need to find the combined partial pressure of gas B and gas C together, we can use the same logic. Since they contribute independently, we add the mole fractions of B and C, 0.25 each, to get a combined fraction. We then multiply that combined 0.50 by the total pressure of 10 atmospheres. The combined partial pressure is 5 atmospheres. Because ideal gas particles do not interact, tracking forces inside any complex mixture is simply a matter of tracking fractions of the whole molecule count.